This is the SpaceX Crew 10 rescue mission from the International Space Station. The mission involves transferring astronauts from the Dragon Crew 10 to the ISS and bringing back Barry, Butch Wilmore, and William, who have been stranded for nearly 9 months. The reason these two NASA astronauts are stranded traces back to Boeing's Starliner. Let's also take a quick look at the thruster problems that has been delaying its return back to Earth. One issue involves the reaction control system, specifically helium leaks. But why is helium so important? Helium, an inert gas, is used to pressurize the propellants that feed the thrusters. If too much helium is lost, the thrusters may not function properly, which could be critical during the flight, particularly in the capsule's propulsion system. During the docking procedure, the Starliner encountered issues with its reaction control system thrusters. The spacecraft's software initially flagged 5 aft-facing thrusters as non-operational, affecting its ability to maneuver in all 6 degrees of freedom. Although 4 of the thrusters were eventually restored, the underlying cause of the malfunction remains unclear. We're here to take a closer look at how SpaceX launch process works, from astronaut transfer to their return to Earth, all the way to landing in the ocean. Falcon 9 is a 2-stage rocket designed for reliability and efficiency. Unlike rockets that rely on a single engine, its first stage is powered by 9 Merlin engines. This design provides an added layer of safety. If one engine fails, the remaining engines can compensate, ensuring a smooth and controlled ascent. The second stage, responsible for propelling Crew Dragon into orbit, is powered by a single Merlin engine. At the very top of the rocket sits the capsule named Crew Dragon, designed to safely transport astronauts to and from space. Just half an hour before liftoff, the fuels and the propellant are carefully pumped into all the stages of the Falcon 9 rocket. The Dragon spacecraft is designed to carry up to 7 passengers. Just below the seating area is the section designated for crew supplies and luggage. Once all crew members are seated, their seats rotate into position, and they are provided with advanced touchscreen displays for monitoring and control. However, the crew does not actively fly Crew Dragon, as it is an autonomous spacecraft. They can take manual control only in case it malfunctions. This is how the launch and ascent stage process works. The Falcon 9 rocket ignites and lifts off, carrying Crew Dragon into space. The first stage burns for about 2.5 minutes before separating and returning to Earth for a controlled landing. Meanwhile, the second stage ignites, propelling Crew Dragon into orbit. This is the orbit adjustments and phasing. Once in orbit, Crew Dragon performs a series of small engine burns to fine-tune its trajectory toward the International Space Station. Gradually, the spacecraft aligns its orbit to match that of the station. Now comes the approach and docking stage. Using its onboard navigation systems, Crew Dragon autonomously approaches the ISS. It carefully slows down and aligns with the docking port before securely latching onto the station using its docking mechanism. Let's look at the hatch opening and crew transfer process. Before opening the hatch between Crew Dragon and the ISS, pressure equalization is performed. Once the hatch is open, the astronauts move into the station, where they are welcomed by the ISS crew. The handover period typically lasts between 3 to 5 days, during which the departing crew trains and briefs the incoming members on ongoing experiments, station operations, and other essential tasks. Once everything is set, undocking initiation begins. Crew Dragon autonomously disengages from the ISS docking port, releasing the soft capture system and retracting the docking hooks of the hard capture system. With a gentle push from springs, the spacecraft slowly drifts away from the station. While this process is automated, manual backup systems are in place if needed. As Crew Dragon moves away, departure burns are performed using its thrusters. The first burn slightly increases the distance from the ISS. Once these burns are complete, the spacecraft enters independent flight mode, meaning it is now flying freely in orbit, preparing for the next phase of the journey. To ensure proper alignment with the re-entry path, facing burns and orbit adjustments take place. Crew Dragon gradually lowers its orbit through a series of controlled burns, positioning itself for the critical D-orbit maneuver. This is a crucial step, carefully calculated by mission control to guide Crew Dragon toward its designated landing zone. The Draco thrusters fire for several minutes, slowing the spacecraft and directing it toward Earth's atmosphere. Before re-entry, this is where trunk jettison occurs. The trunk, which houses the spacecraft's solar panels and radiators, is detached and left to burn up in the atmosphere, while the capsule continues its controlled descent. As Crew Dragon enters the atmosphere, it experiences the most intense phase of the journey. Traveling at speeds exceeding 17,500 miles per hour, the capsule endures extreme heat and pressure, with its heat shield providing protection. The buildup of plasma around the spacecraft causes a brief blackout in communications, a normal but dramatic part of re-entry. Once the fiery descent is complete, the parachute deployment and splashdown sequence begins. At around 18,000 feet, which is around 5.5 kilometers, 2 parachutes deploy to stabilize the capsule. Moments later, at 6,000 feet, this is around 1.8 kilometers, 4 main parachutes fully open, ensuring a smooth and controlled descent. Crew Dragon then splashes down in either the Atlantic Ocean or the Gulf of Mexico, depending on weather conditions. After splashdown, recovery and crew extraction operations begin immediately. SpaceX recovery teams quickly arrive by boat, securing the capsule and assisting the astronauts. Following medical checks, the crew is transported back to land, marking the successful completion of their journey home. Let's take a look at this $1.5 billion Boeing Starliner with a capacity of carrying 5 crew and the difference between the other capsule at the Russian Soyuz and SpaceX Crew 10. Unlike its counterparts such as Musk's SpaceX Dragon or the Russian Soyuz, the Starliner is designed to land on solid ground rather than in the ocean. It accomplishes this by deploying a combination of drug parachutes, then releasing the main chute and finally deploying airbags to land on hard surfaces, cushioning the hard landings. Here are the height comparison between the various spacecraft along with an average human to help you understand the scale better. For further comparison, we can place the SpaceX Crew Dragon and the Russian Soyuz spacecraft beside the Boeing Starliner. Interestingly, the Starliner weighs a staggering 978,924 pounds, which translates to around 44,000 kilograms when fully fueled for launch. To give you an idea of how heavy this is, consider this school bus, which weighs around 36,000 pounds. This means the Starliner's weight is equivalent to almost 27 buses. That's a tremendous amount of weight, as it is much smaller than its counterpart.